I won't go much into my background. I'll just launch into this next presentation, which is it's a bit an unusual, maybe, at least for me. It feels a bit unusual. It's a bit of an opinion piece. This is about unlocking parallel performance through types. And this actually goes back to things that was very nicely placed already by Philip, so thank you for that, and also some stuff that Joe was talking about this morning. So this is now going over lots of joint work done with lots of other people, local people at Uppsala University, some people at Stockholm University, some people at Imperial College, and Microsoft Research Cambridge. Okay, so the starting point here is really this question, are programming languages aligned with how programmers use them? I mean, essentially, the freedoms that the languages give us, are they freedoms that the programmers use and take advantage of? And so this is based on some studies done by PhD students of mine. So we can start by looking at some Python code. So these are now 35 Python programs. It's about 500,000 lines of Python code combined all together. And this is showing the place in the program that sees the most possible types. Right? So if you have a call on a method, like x.m brackets, you call a method on some x, what are the possible types of x during the run of the program? And we can see that in these programs, some extent of megamorphism exists everywhere. So like some of these programs have 350 types passing through in just one line of code. Others have about maybe 6 or 10 or something, but still a fairly high number. And that's possibly in line with how one might think about the Python program. It's a dynamically typed language. You can do pretty much whatever you want. You can change things, types on the fly, rewrite lots of stuff. However, if we look at how often programmers actually make use of this dynamism, it's in very few places of the code. So if you take one of the, let's jokingly call it one of the world's most boring type systems ever, the Java 6 type system, and we say, let's take your arbitrary Python program and try to type it with Java 6 without even interfaces. Like how far can we get? And it turns out we can get really far. So this is the same 35 Python programs now, sadly, slightly different order, doesn't really matter. The whole point here is that these staples are showing to what large extent could we slab a static type on each line of code that performs a method call and capture all the variants, the call site variants there. And it's about 90% for all of these programs. So this, even though there are places where you can use 350 different types that flow through one line of code, still those are in a very limited amount of places in the program, and most parts of the programs are actually, they're like Java programs written in Python. And whether this is because universities educate programmers as Java programmers and then they program in Python, or something else that I can't really say anything about. All right. Similar study now on Java programs, studying different properties. So if you run, as in this case, this is a study based on 1 million lines of Java code plus libraries. This is just taking one pretty picture out of that study, because I can't fit them all on the slides. If you look at properties of the Java objects, such as whether they are pointed to from lots of places, whether they are ever modified in the system, those things that you would expect from your run-of-the-mill imperative object-oriented programming language, these things seem that they quite rarely occur. So looking at this picture, this is showing all the, oops, I should not have done that. I don't know what I did. Oh, now I undid it, so that's good. I'm sure there is some form of laser beam on this one, but I don't know what the button is. Oh, is that the one? Yes, okay, good. So here, all these green objects are objects that are only being pointed to by one other object in the system. So we know exactly, like we're following one reference, we end up in this object. Follow any other reference, you can't end up here. If we look at all of these red objects here, they are immutable, so they will never be changed ever in the system. If we look at the orange ones, they are stationary. That means that if they are ever read, they will never be written again. So first time we read them, they are immutable ever after. Right? Okay, so these are fairly strong properties that are quite useful. And if you look at the amount of plain old Java objects, in the sense objects that are being referenced from lots of places and mutated, they are somewhere here. So it's a small number, surprisingly, at least to me, small number of objects. So the takeaway point here is that most objects are not modified, nor are they aliased heavily. So that means really that a majority of all the objects in those particular Java programs that we studied, they were either immutable, or they weren't aliased, or they were stationary, meaning never mutated after first time read, or several of these properties. And another nice thing that came out of this study is it seems that all of these properties that I just talked about, they are per class. So this doesn't really show as nicely. This is using the colors now coming out of this tool that Stefan, my PhD student, built. But this is now checking per class. How common is it that if one object instantiated from this class is immutable, say, that all other objects instantiated from the same class is also immutable? And it turns out it's a per class property. So we, as programmers, we design classes knowing that this thing will not be shared, or this thing will not be mutated, or this thing will not be mutated after read, and there are other properties like this as well. So that means that we can pretty easily describe in the code these properties, right? It's just essentially a matter of one annotation per class. So that's nice, right? So what if these properties then were guaranteed at compile time instead, right? So it seems that there's this fundamental, let's say, distance between what is captured standard by the language, what's allowed by the language, and how programmers use it. So what if we sort of aligned what the language tells us of our programs with how we actually program? What could we do? So that's an interesting question. Some of the things we could do, for example, is we could have compile time guarantees for data race freedom, right? That's something nice. It's also something that came up in Philip's talk, for example. Or we could use this information at compile time to make the compiler be either more aggressive in its optimization, or perhaps rule out some optimizations where they might not be sound, and that would be something that Peter could tell the implementer of the compiler then probably. Right, or we could leverage this information to build runtimes, which is more efficient because the runtime can rely on certain properties holding at any point in time. That's nice. Or we could actually just flip the defaults of the plain old Java objects. Maybe shared should not be the standard. Maybe mutable should not be the standard, since it doesn't seem to be the thing that crops up most of the time for most objects in a Java program. So that would be fun. So I'll go through some examples of stuff we're doing that's kind of exploring this direction of aligning the languages more with how people actually program in them. So this first one is attempting to get data race freedom guarantees at compile time. And this is work done mostly by Elias, who is a PhD student of mine. So he's building this system. I'm going just to give you a very, very shallow overview of what is happening here, because really there isn't that much time to go into any depth. But so what Elias is doing is taking a traits-based programming language, right? Essentially where your classes are being built up by smaller building blocks, essentially interfaces with code, if you think of them like that, which is incidentally what interfaces are like in Java 8, right? And you can decorate each interface with some property that we call a reference capability. So there are lots of properties. Let's call them unaliased, thread local, locked, read-only, or encapsulated, for example. So these are now properties that we can slab onto our traits, and then we can take our traits and we can form classes, and then we can sort of parameterize this composition over these labels, right? So we can have two traits, one to increment a counter value and one for reading it, just taking a very, very minimal example. And we can build lots of different types of counters using these building blocks without changing anything except those colored boxes. Right? So we could, for example, build a local counter. So this is a counter now that's going to live in one thread only, and the type system is going to tell us immediately if we break this constraint. So here is now a local counter. It's thread local, can only be referenced by one thread. It can be aliased freely, multiple. We could have multiple accesses, well, not concurrently, of course, because it's thread local, but we could have multiple things reading the increment part, so the read-only part of this at any point in time, because it's only reading, right? So if we're reasoning about the correctness of a program, we can sort of rule out this situation, because this alias of the counter across two different threads could not happen, right? Or we could build a counter that's shared, and in this case now it's going to be protected by a lock. So there is a lock, oops, I did it again. There is a lock on this increment capability, and there is a read label slapped onto this reading capability. And from this, the compiler will actually be able to say, okay, good, we can access this because, for example, we won't have any races on concurrent increments or concurrent increments and gets or anything like that. And we can even sort of derive a reader's writer lock for this particular class that will govern the variables that are shared across the different building blocks. And we will also have a static guarantee that this is actually used correctly. So you won't grab the read lock and then try to write. The compiler will shoot that program down. Or we could use even more fancy stuff. We could build up your average sort of fork join parallel program where you have a tree, and the tree is built up by things that in this case are not aliased, and then the compiler will be clever enough to figure out that we can in parallel do all of these standard fork join style operations on these objects, because we know that there is no aliasing across the nodes, there is no aliasing, there is no aliasing across the elements, and there is no unsafely aliased elements, meaning there is an element here that sort of is shared by possibly some other thread in the system, right? And it doesn't have to look super weird, right? And I'm showing you the weirdest code that I can for this. So this is a for each loop, sort of similar to what Philip had, I think, in his presentation. And it's saying, if you lend me a tree, then I will take this tree, I'll split it up into 3 different parts, the left branch, the right branch, and the current element. And then using fork join style parallelism, I'm going to recursively operate on this. And that's nice. It's not too alien, but we can even do better because of this nice property of these things being per class, right? So all of this unaliased bits, they are really stuck up here in the declaration of the tree class, so they can be inferred. So we can just use local type inference to do something like that. And we could even go further and say, hey, we could deduce that this splitting can take place. So essentially, the compiler will be clever enough to figure out that the program could have been written like that, but really, it's written like that, which is what we would have written probably from the start in Java. And this all falls out fairly nicely by, again, taking a more restrictive approach to sort of the standard behavior of classes, methods, etc., in an object-oriented programming language. Okay, moving on to the next example, which is using these types to build efficient runtime. So we had some super nice examples from Philip from the previous talk that said, look, we can, with not that much work, we can get a type system into Scala that will allow us to show that we have this actor isolation, for example. So that's really nice. And like we're doing something similar. This is stuff done in collaboration with Imperial College and Microsoft Research Cambridge, and Sylvan is the main driver of all of this work. So if we take again the concept of an actor-based system, so actors, concurrency abstractions, as Philip has already explained, each actor is single-threaded, but we have lots of actors in our program, so the programs thus become multi-threaded. And we need this actor isolation, as Philip already explained, because otherwise, how can we know that the actors are single-threaded? Right? If this actor can follow this reference and end up reading this thing, right? And there is a thread here indicated by this beating heart that I found, and another beating heart in here, then they can both race on this object at the same time, and hell will freeze over or something else. So we need some form of isolation, or we could, of course, do essentially what Philip talked about. We can allow this actor over here to reference this object over there, provided it's, for example, immutable or something like that, or it's stationary. And if we have this property of non-aliasing, then the isolation falls out more or less for free. So that's nice. However, if you put this, let's say, into Scala and you run it on top of the JVM, you'll still end up in a situation where, like, the underlying virtual machine knows nothing about this isolation across the different actors. So to the JVM, this is a whole big heap anyway, and in order to do garbage collection in this heap, we'll have to consider the whole heap as a single unit. And this is what Joe was talking about this morning when he said, let's copy stuff so that we can do garbage collection in parallel. Right, so Java has this big single heap, and we could, of course, do a simple stop the world collector, or we could have a concurrent collector. But if we do have a concurrent collector, we'll need to cater for the fact that other threads might come along and sort of interfere with garbage collection while it's running. So enters now this Orca system, which was mostly a design by Sil and Klebsch that I already mentioned. So, which is a sort of a GC type system co-design. So now we're going to build garbage collector that works by sort of knowing how this, by leveraging on these guarantees that we got for free when we were compiling our program. Right? So we have a system where we have lots of actors. The actors own their local objects. They can share these local objects freely, but by using sort of the cleverness of the type system, we can do copyless message passing. Right, so we can go into this in some detail. So we have this red, the red actor over here, and it's sharing some of its local objects with the blue actor. Right? So in order to do this in the Orca system, the red actor needs to mark that all of the things that it's sharing, so it's A, and then A, of course, leads to B, and B leads to C. There is now some external stake in these objects, and we're going to represent this external stake by some abstract value M here. Right? Now, blue can share this stuff with the green actor, and it can do that without synchronizing with the owner, the red object, by just transferring some of its stake over to the next actor. So now the green actor has a stake of n in these objects, and the blue actor captures that by sort of decreasing its stake in these objects. At some later point in time, the green actor loses its last reference to these shared objects, and right now it doesn't actually have a stake in it in practice, although it still thinks so. At some point, its view on its own heap becomes consistent because garbage collector triggers, and we see, oh, hey, I don't have A anymore. Okay, good. So I should tell A's owner that I'm no longer interested in A's owner, in this case red, keeping this alive. So it'll send a message saying, oh, I don't need A anymore, so decreasing its stake in A. Right? And so now the model becomes consistent again, and you can see really that the nice property here is that the owner's view of the external stake in this object and the world's view of the stake in the object will be the same value. Right, so good. When this counter now reaches 0, we know there's no one else interested in these objects, so that's great. Now I can do garbage collection in my own local heap, just as you would in Erlang, for example. So that's nice. I'll have to basically skip over this slide now for lack of time. But the nice thing, what we can ask the question, what happens if everyone else is garbage collecting like crazy at the same time? Won't we have concurrency problems? Well, no. Here's where the type system comes in to save the day, because the type system will say, if I have a pointer to something, then no one else will have a pointer to that same thing through which they can write. So we're all sharing this read-only style. We can just traverse it fine. We don't need to care about what the program is doing anywhere else. Or if I have a pointer to an object through which I can write, I know no one else will have a pointer to it through which they can read. So again, I can go ahead and I can scan it, and I don't need to synchronize with anyone else. And a bit of snake oil always is nice. So we can get this to perform really nicely. And this is, of course, benchmarks running in a very sort of small environment. So you shouldn't build too much from this. But it seems that we can do well on GC-induced jitter, and we seem to scale quite nicely. And I'm happy to talk about these slides offline later. This thing I'm not even going to get into, so luckily I took already out the slides, but you can also do interesting things with cache-efficient memory layout, again, if you have more control of what the system actually does to your objects. So, final slide. So, by essentially aligning the programming languages with how people seem to be writing programs anyway, we could more or less for free, and that's at least the idea, of course. We have studied some programs, we have a feeling for this, but we need to study more programs to see that this actually is as widely applicable as we hope or believe. But we can change the programming languages so that they give us more guarantees, and we can use these guarantees to do interesting things. We can get away from data races, we can build more efficient runtimes, etc., etc. And I think I'm done. Thank you.